We introduce a new sensor for velocity estimation for autonomous underwater vehicles based on differential pressure. The inclusion of our sensor in the navigation suite for AUVs can have impact in two significant areas. The first area is state estimation for autonomous navigation. The combination of different velocity sensors with different error characteristics can improve the velocity estimation and, more generally, the navigation performance of AUVs. Furthermore, the introduction of an additional independent option to estimate velocity can increase redundancy of the system, which is specifically important for long-term and deep water applications. Additionally, velocity estimation capabilities can be increased for small-scale and low-budget vehicles that cannot employ state-of-the-art velocity sensors, such as with Doppler velocity logs. The second area is the in-situ estimation and measurement of environmental features, such as ocean or tidal currents. For instance, by combining velocity measurements relative to water with velocity measurements relative to ground, ocean or tidal currents can be measured in real time with a much finer granularity compared to remote sensing or ocean models. Building upon previous work that introduced the first version of the Differential Pressure Sensor Speedometer (DPSS), we built a second version which is smaller and lighter. As opposed to the previous version, DPSS version 2 is designed as a standalone system that can be attached or integrated to any kind of AUV. DPSS version 2 consists of a 3D printed housing, 2 differential pressure sensors, a LiPo battery, a 9 degree of freedom IMU, a microcontroller for signal processing and data logging, and an absolute pressure sensor. So how can we measure 2D velocity based on differential pressure? Based on the assumption of a planar, inviscid, irrotational, and incompressible flow around a spherical object, we can employ potential flow theory to solve this problem. More specifically, we can use Bernoulli's law to relate pressure at the spherical body to free stream velocity. We employ a variation of the directional finding pitostatic concept and estimate surge velocity and the angle of incoming flow based on the pressure differences between points A and B, as well as A and B star as depicted in the figures. To verify the efficacy of the new prototype under field conditions, we conducted tests in the Trondheim Fjord in Norway. The right image shows the tidal current patterns for the upper fluid layer during the flood tide. The flow patterns reveal several large circulation areas in the fjord. To be able to predict reasonably well the directionality of the tidal currents, a test site outside of those bigger circulation patterns was chosen. The area that was chosen was located towards the upper part of the Trondheim Fjord, where the landscape forms a broad natural channel. Here the ocean currents were expected to approximately run parallel along the coastline. However, as the two images to the right show, the current direction and magnitude are dependent on the tidal cycle, which needed to be taken into account during the analysis of the experimental results. Finally, the test site, which is marked with the red dot, was chosen to be close to the island of Tautra. The DPSS version 2 was attached to a light autonomous vehicle that had a DVL on board. The vehicle's navigation was based on its onboard sensors and a predefined trajectory, while the DPSS version 2 was independently logging data. The LAUV was programmed to dive to 15 meters and then follow a straight line in the approximate direction opposite to the estimated main current direction for a specified amount of time. After surfacing, the AUV reversed its direction and followed a straight line trajectory along the estimated direction of the tidal currents. Aside from the LAUV, a boat with an onboard acoustic Doppler current profiler was used to get an independent estimate for tidal current direction and magnitude. The boat with the ADCP was approximately following the same trajectory as the LAUV. In total, 14 trials were conducted with varying target body velocities for the LAUV. The tests were conducted shortly before, during, and after high tide. Therefore, changes in the current magnitude and direction were expected. While tidal currents were directly estimated by the ADCP, the current estimation based on sensors on the LAUV needed the combination of different velocity measures. Both the velocity estimations of the DVL in waterlogged mode and of the DPSS version 2 were combined with the estimates for velocity over ground by the DVL in bottom-lock mode to compute tidal current estimates. The following results for the tidal current estimates from the LAUV sensors are depicted by DVL waterlogged versus DPSS, with the implicit assumption that both depended on the DVL bottom-lock measurements. The figure shown here displays the median and interquartile range for the current magnitude estimation of DPSS, DVL, and ADCP for each trial. The left side of the figure represents results of trials conducted before high tide, while the right side of the figure displays results of trials conducted after high tide. It can be seen that the tidal current estimations of DVL and DPSS are in more agreement and have less variability compared to the ADCP data. Normally, ADCPs are applied to measure river currents, and the same area is traversed several times in relatively calm waters to get a robust result. In our test, the ADCP was subject to surface effects such as waves, to salinity gradients, and it followed the straight line trajectories of the LAUV without any repetitive transects. After consultation of expected current magnitudes based on coarse model prediction and based on the better summary statistics of DPSS and DVL, only DPSS and DVL tidal current estimates were analyzed further. To get a better understanding of the effect of relative orientation between the tidal currents and the movement direction of the LAUV, velocity estimates from DPSS version 2, DVL in bottom-lock, and DVL in waterlock were directly compared. The figure shows the velocity estimations for a trial that was conducted approximately against the current direction and for a trial that was conducted approximately with the current direction. For the trial against the current, it can be seen that for both surge and sway velocities, the DPSS and the DVL waterlock estimates are closely aligned. The DPSS estimates are even smoother compared to the DVL in waterlock. In contrast, for the experiment along the tidal currents, the DVL waterlock and the DPSS estimates diverge. Since the tidal current component is superimposed on the direction of movement of the vehicle and essentially applies to the back of the DPSS, the potential flow assumption does not longer hold, and the DPSS measurements are not longer reliable. This clearly shows the limitation for the water relative velocity estimation of the current prototype. The next figure clearly shows how the redundancy and estimation quality can be improved by adding another source of velocity estimation to the navigation suite of an AUV. For an unknown reason, the DVL measurements become unreliable between 55 to 65 seconds, while the DPSS estimation is unaffected. This figure shows magnitude and direction of the tidal current estimates between DVL in waterlock and DPSS version 2. It confirms the analysis of the velocity estimates because it can be clearly seen that the DPSS estimates along the current direction are far less reliable. However, the estimates against the tidal current agree very well with the DVL measurements. Additionally, it can be seen that the tidal currents change direction and grow in magnitude over time, as an effect of the transition from tidal rise to tidal fall. We believe that the DPSS version 2 can be seen as a step towards a compelling complement or occasionally alternative for velocity-aided navigation and in-situ environmental monitoring for AUVs. Future work will concentrate on 3D velocity estimation with the DPSS, on lifting the directionality restrictions, and on the detection of environmental clues beyond ocean currents.